Hi everyone, I'm Will Rosenbaum, and I'm excited to talk to you today about some joint work with Christine Cheng entitled Stable Matchings with Restricted Preferences, Structure, and Complexity. So let's get started. So just a quick overview of my talk. So first I'll describe some background and motivation. I'll describe our main results. I'll give a little hint of the methods that we use to get the main results. And then finally, I'll mention a few open problems at the end of the talk. So let's get started with background. So we consider the classical stable marriage problem. So we have two sets of agents traditionally referred to as men and women. So I have men in blue on the left and women in red on the right. And each agent has preferences in the form of a ranking of the agents of some or all agents of the opposite sex. So in this case, man A prefers in order woman A, C, B, and then D. And we want to find a matching between the men and women, but we want to find a particular type of matching. And what we want to avoid is the case that a pair of agents mutually prefer each other to their assigned partners. For example, with this matching, man A and woman C mutually prefer each other to their assigned partners, so they form what's called a blocking pair. And so this matching is not stable, and we want to find one that is stable. So for this instance, we can find a stable matching just by assigning each man his top choice woman, and we arrive at the following matching. So this problem was studied by Gale and Shapley in their seminal work from 1962, where they describe an efficient algorithm that always finds a stable matching. In particular, this means that stable matchings always exist for all preferences. However, the Gale-Shapley algorithm is somewhat limited, so it finds at most two distinct stable matchings, one of which is optimal for the men and pessimal for the women, meaning it's each woman is assigned her worst partner among all possible stable matchings. And by reversing the roles of the men and the women in the algorithm, we can find a matching that's optimal for the women and pessimal for the men. But in general, there might be exponentially many stable matchings. So we might want to find matchings, for example, that are more fair in some sense. So this raises a few questions. So first of all, we might want to know how many stable matchings a given instance has. So this is a very natural computational problem that we might ask. Another question is whether we can find matchings that are more fair in some sense. And this is studied in a lot of works, and there's a lot of different notions of fairness. But a few that we consider in this paper are median stable matchings, balanced stable matchings, and sex-equal stable matchings. There are a bunch of other notions of fairness, but these are three that we consider. Another question we might ask is if we can even sample a uniformly random stable matching and perhaps form a mechanism by reporting a random stable matching. To address these questions, we have to understand the structure of stable matchings, so we'll get into that. So the structure of stable matchings is elucidated by considering rotations. So here is the matching instance that we had before. And what we can do is, starting with, say, man A, look down his preference list for the first woman that appears later on his preference list from his current match, who prefers him to her assigned partner. So if we look at woman C, so she actually prefers man A to her current match. Then we can look at woman C's partner, man C, and do the same thing. Look for the next woman on his preference list that prefers him to her assigned partner. We arrive at woman B. Then we can look at B's current partner, man B, and see the next woman on his preference list that prefers him to her assigned partner, and we get back to A. So we now have this kind of cyclic list of pairs, AA, CC, BB, where we can actually arrive at a new stable matching by cyclically permuting the pairs. So this is what's known as a rotation that's exposed in this matching. And if we assign the new matching based on the previous gray dotted edges, we get a new stable matching that's worse for each of the men involved in the rotation, but better for all of the women. So this notion of rotation was introduced by Irving and Leather in 1986, and they showed that all stable matchings can be obtained by eliminating a sequence of rotations. So this process of doing the swapping of spouses is known as eliminating the rotation. And they also describe a natural precedence relation on the rotations, which they refer to as the rotation poset, or partially ordered set. They prove that stable matchings are in one-to-one correspondence with downsets in the rotation poset, and they prove the following theorem. They show that rotation posets can be efficiently computed from the preferences, and they show that every finite poset is a rotation poset, in the sense that they describe an algorithm that if you give it a finite poset, it will construct a stable matching instance whose rotation poset is isomorphic to that the given poset. So using this structural understanding of the structure of the set of stable matchings, we can show that certain problems are computationally hard, NP hard. So Irving and Leather initially showed that the problem of counting stable matchings is NP hard. In fact, it's what's in this class known as Sharp-P complete problems. And subsequent work showed that finding median, balanced, and sex-equal stable matchings are also NP hard. And the proof technique for all these results is the same. They give a reduction from an equivalent hard problem on the rotation poset. So the slogan for what's going on here is that the structure of the rotation poset determines the complexity of the associated task related to stable matchings. So this raises a natural question, as I think all computational hardness results do, which is, do these hard stable matching instances arise in practice? So we address this question by considering restricted preference models that are motivated by applications to matching markets. So we consider 4 restricted preference models. First, the K-bounded model, then the K-attribute model, the K1, K2 list model, and the K-range model. And I'll describe what these models are in just a second. But the K-bounded model is kind of implicit in early work in stable marriage, in the stable marriage problem. But the others were introduced by Bhatnagar et al. In their 2008 paper. So K-bounded preferences are as follows. A stable matching instance is K-bounded if all preference lists have at most length K. And the motivation here is that, at least in all matching markets that I'm aware of, it's actually rarely the case that one would rank all possible partners. So we look at a very restricted setting where everyone's preference lists are very short. In the K-attribute model, each agent is assigned a profile. So an agent A has a profile VA, which is a vector in K-dimensional space, and phi A, which is a linear function from points in K dimensions to the real line. And A ranks potential partners B according to this function phi A. So A applies phi A to B's corresponding vector and ranks B according to that value. So the ranking is decreasing according to phi A. So the motivation here is that these preferences arise in ranking by questionnaires, for example, in dating websites. So so VA encodes an agent's own responses to questions in the questionnaire, while phi A encodes the desired responses of an ideal partner. So in this case, K is the number of dimensions or the number of questions in the questionnaire. We then consider this K1, K2 list preference model, where men and women are partitioned into K1 or K groups respectively, and all agents within each group have identical preference lists. So the motivation here is that you might have preferences that can be inferred from some group identity. So for example, prospective computer science majors might adopt the same rankings of universities according to the perceived strength of those universities' computer science programs, but these would be different rankings than, say, prospective majors in other disciplines. And finally, we consider this K-range preference model, where for each woman, W, the men's rankings of W differ by at most K-1, and symmetrically, each woman ranks each man similarly. So the motivation here is that preferences might be derived from some master preference lists, say some objective measure of preference, but there's some slight noise, so you can deviate from the objective lists by a small amount, by at most K-1. So the main question that we ask then is, for these restricted preference models, what rotations are realized? And in particular, we want to know, can we exploit the restricted preference structures to give efficient algorithms for some instances of problems that are known to be hard, say NP hard, in general? So what are our main results in this direction? So first we have some hardness results. So our first theorem is, given an arbitrary finite poset P, then there exist stable matching instances in the following models that realize P. So in the K-bounded model for any K greater than or equal to 3, in the K-attribute model for any K greater than or equal to 6, and in the K-infinity list model for any K greater than or equal to 2. And what I mean by this K-infinity list model is that, say, the men can be partitioned into K sets where within each part, the men have identical preferences, but the infinity indicates that there's no restriction whatsoever on the women's preferences. For all these cases, we can compute instances from the poset P in polynomial time. So this shows that the structure of these restricted, the structure of the posets of these restricted preference classes is actually completely generic. So as a result, we get consequences for the computational hardness of problems. So in these restricted preference models, all structural problems are as hard in the restricted preference models as they are for generic or general preferences. And by structural problems, I just mean a problem whose output depends only on the structure of the rotation poset. So in particular, we have that counting stable matchings is as hard, it's BIS complete, or sharp BIS complete, for these restricted preference models as it is in the general case. Also, finding median stable matchings is also sharp P hard. So this may be somewhat surprising because these preferences are very restricted. It says that even if people are only allowed to rank at most 3 potential partners, it's already as hard to count the number of stable matchings as it is if we place no restrictions on the preference whatsoever. Similarly, even if our dating app questionnaire only has 6 questions, it might be as hard to find a median stable matching between the men and women as the general case. For the K-range model, we actually get some algorithmic results. So for any constant K, the rotation poset of every K-range instance has bounded path width. So this is a way of saying that the structure of K-range rotation posets is highly restricted. So this is unlike the other preference models. And in fact, we show that the path width essentially characterizes the rotation posets that can arise in the K-range model, because we show that given any poset P with path width K, we can efficiently construct an O of K range stable matching instance that realizes P. So as a result of this, we can actually show that a lot of problems that are NP hard in general have efficient algorithms on K-range instances. So for example, we can efficiently count and sample stable matchings. We can find median, balanced, and sex equal stable matchings in any K-range instance very efficiently, whereas in general, these problems are NP hard. So the takeaway messages from this are that for small k, k-bounded, k-attribute, and k-infinity list preferences realize all finite posets, and as a result, structural problems are as hard as for the general instances. On the other hand, for the K-range model, the the rotation posets are highly restricted, and computational problems may be significantly easier than the general case. So I just wanted to give a quick indication of some of the methods, in particular the methods we use in the construction of instances realizing particular posets. So given a poset P, we want to construct a stable matching instance with rotation poset isomorphic to P and preferences from a chosen restricted family. So here's a picture of an instance where we have 4 men and 4 women. The men are in blue, the women are in red. And we have each agent ranks its 2 neighbors in the picture on the right. So the man-optimal stable matching consists of the blue edges. So the men prefer the blue edges, the women prefer their red neighbor. And we can eliminate the bottom rotation and arrive at a stable matching in which the women on the bottom are matched with their vertical neighbor. Or we can eliminate the top rotation and get the red edges on top. Or we can eliminate both rotations and get the woman optimal stable matching. On the other hand, if we add an edge between the man and woman on the left, the green edge here, and set the preferences so that this middle edge is preferred between the blue and red edge for both the man and the woman, then the upper rotation is no longer exposed in the man-optimal stable matching. So if I have the blue matching on the bottom and the red matching on top, then the green edge becomes a blocking pair because both the man and the woman on the left prefer the green edge to their partners. So by adding this green edge, we actually enforce a precedence relation between the 2 rotations. So sigma, the upper rotation, is only exposed after the bottom rotation has been eliminated. So this instance realizes the new rotation poset indicated on the left, where the bottom rotation needs to be eliminated before the top rotation is exposed. We can generalize this procedure. So if we want to, for example, realize the rotation poset on the left now, this kind of diamond shape, we can add 4 rotations on the right and add these green edges to force the precedence relation. So that's the basic idea of the construction. In the paper, we formalize this gluing together of rotations to force precedence relation. And we give a generic construction where for each poset, we can create many instances realizing the poset. And some instances are in the preference models that we want to consider. So I wanted to just leave you with a few open problems that we weren't able to resolve in this paper. So the first is understanding the rotation posets for K1, K2 list preferences, where both K1 and K2 are finite. The second question is generalizing to preferences with ties and indifference. The third question is to understand the structure of stable matchings on restricted graph families, for example, planar graphs or bounded genus graphs. So that's everything that I wanted to say. So thank you very much for listening to my talk. And I look forward to hearing from you if you have any questions or are interested in following up on this work.